Okay, thank you. Can you hear me? So thanks a lot to the organizers for inviting me and to speak, to give me the chance to speak here. So I'm going to talk about celestial and Carrollian amplitudes and also some connection to Liouville theory. So why should we be interested in celestial and Carrollian CFTs? Well, they are a good setup, or they provide a good setup to study asymptotic symmetries like BMS. And as such, they serve as bottom-up approaches to build candidates for holographic duals. I mean, which leads to flat space, or which aims towards flat space-time holography. And as such, you might, this series is conformal, since you have conformal series, you might hope to constrain the S matrix in a better way, or to understand more about the S matrix than in 4 dimensions, and understand amplitude relations which you don't understand in 4 dimensions. And the reason why you hope so is because these amplitudes are sensitive to both UV and IR physics, and that leads to powerful constraints, as we will see, on the analytic structure of the amplitudes. So let me first set up the stage for celestial sphere, and then for Carrollian geometry in 3 dimensions. So we start with the Minkowski metric and write it in Bondi coordinates. So we have here with the retarded time coordinate u, and then actually the celestial sphere you see when you just sit here and look in the sky. I mean, for example, at r is equal to 0, then you see this celestial sphere. And in the Penrose diagram, it looks as follows. So you here at r is equal to 0, you look at the sky and you see the celestial sphere. And actually, I draw here the Penrose diagram doubled. So, I mean, of course, 1 triangle would be enough. But there's this antipodal mapper, which maps this green point to this green point here, and that's why I draw it, this diagram doubled. But actually, when you look at the matrix, there's an issue, or that actually this antipodal map, this point here, gets mapped to the point here, which corresponds to the Penrose diagram with the advanced coordinates, and advanced coordinates v. But any massless particle will hit the celestial sphere. You only have to wait, and that means so at some point it will hit this point. So that is, means that these points are natural arenas for in and out states for asymptotical scattering processes. Now, so I will only discuss massless particles. As I said, the massless particle at some point will hit the celestial sphere, and you can compute this coordinate where it hits the celestial sphere. So you have a massless particle in 4 dimensions, which is given by 4 momentum p. So it fulfills the Marshall condition. So you have three independent real variables p, and then you can map them to this new variable. So z is given by this point on the celestial sphere, and omega is the energy. And of course, you can invert this map and then write the momentum in terms of this null vector q. And the null vector q will play a role, a very important role later on. So this is, of course, a triviality, and applying this coordinate transformation on the plane wave in Minkowski space, you will see that now, rather than dealing with plane waves, you will deal with boost eigenstates on the celestial sphere. And this has far-reaching consequences, while these are, of course, constructed as eigenstates of translation operator. Here, I mean, you you don't see translation invariance as easy on the celestial sphere. To wrap up, as I said, this two-dimensional conformal celestial conformal field theory is a natural setup for establishing or studying BMS symmetries, and so you can study global BMS symmetry and local BMS symmetry, and you can represent the generators. So you have a full Virasoro algebra describing conformal transformations, and then you have also translation operators. And as I said already before, translation is a little bit peculiar on the celestial sphere, so it mixes. This will be the conformal weights on the celestial sphere, so it will mix this holomorphic and anti-holomorphic sectors of Z and Z bars. And you can also study or construct the algebra for extended super BMS extended super BMS symmetry, as we have done some years ago. And so there's a nice representation of this symmetries in terms of conformal primary operators of the underlying conformal celestial conformal field theory. Now, one question. I mean, it's not. There's no supersymmetry in 2 dimensions. I mean, you start with 4-dimensional in 4 dimensions, and you construct there. You have super multiplets, and then you study. You construct the operators, and then you find that the spin 3/2 partner and spin 1/2 partner of this stress tensor will fill up the super BMS algebra. Now there's no extended in 2 dimensions. I mean, we don't see it on the celestial sphere. The supersymmetry. Also, we have super multiplets in the 4-dimensional. I mean, we study amplitudes in 4 dimensions, and then we construct Ward identities from which we extract this algebra. Now, you might have seen, you might have anticipated already that there's this issue with the antipodal map, that we have 2 patches of coordinates. And now, in the Carrollian approach, we take not only the celestial coordinate C and C bar, but we also take the retarded coordinate U together as our target space or to study. But the U is a null line, and therefore the induced metric on this Scri plus degenerates. So it takes the form of a Carrollian geometry. And so we have an induced Carrollian geometry at Scri plus minus. So that's exactly what is nice for us, because we know that the conformal Carrollian group in 3 dimensions is isomorphic to the BMS4. That means again, it's a nice setup. This Carrollian geometry in 3 dimensions, a nice setup to study flat space-time holography. I mean, get some dual description of flat space gravity in 4 dimensions. I mean, there's this beautiful paper by Laura, Adrien, and Romain, and Avray. So I'm quite new in Carrollian physics, so I'm still studying this paper, and it's a beautiful paper. But that is so far what I understand about this Carrollian geometry, what I tell you here. So if you have more questions, I think it's better you address the question to them. Anyhow, so what I have said is that, or what is important, that we have this symmetry, and for example, the local conformal transformations now can be expressed in terms, or can be written in terms of this generator. So on the celestial sphere, we had just this operator, and now we have just the U dependence in addition, and you can construct a similar operator for translations, which is now nicer on the Carrollian space than on the celestial sphere, but so it doesn't mix this holomorphic, anti-holomorphic sector. So now we have what are our states in both approaches, Carrollian and celestial. So we have like just take a plane wave, and we can construct these operators by this Mellin transformer. And this gives us some wave function or some conformal primary depending on this celestial coordinates z and z bar and axis four-dimensional space-time coordinates. And when you look at the spectrum of this operator, you will see that the dimensions are constrained to be 1 plus I R, but actually you can relax this condition by analytic continuation. But so this is how you construct the operators in the celestial approach by performing this Mellin transformation. And in the Carrollian setup, as has been shown by these two groups, you do, rather than a Mellin transform, you do a Fourier transformer, where this U coordinates, this retarded time coordinate U, this null line enters here. And so this develops this dependence on this third coordinate, U. And of course, now you see that you have the same space, dimension of space, because here you are if you constrain here to real numbers. So it is just one-dimensional real. This corresponds. So you have here three coordinates, and here you have 3 coordinates as well as the real coordinates. And this will play an important role because, as has been pointed out by this group of people, is that you can switch between the two approaches through this integral transformations. So you can switch once you have, for example, your celestial amplitudes. You can combine this inverse Mellin transform together with this Fourier transformation to arrive at Carrollian amplitudes, for example, or Carrollian states. This is a Fourier transform. What is the comment? No, I don't give you credit for this. I give you credit for that that you stated very clearly in your paper that you can switch between these two approaches. Okay. Now, of course, we need to understand this celestial and Carrollian CFTs better in order to start the program about flat space-time holography. Eventually understand, for example, this amplitudes better. So that means we need to understand the nature of this underlying conformal field theory. So of course, a conformal field theory means you need to understand spectrum and interaction and so on. And there has been, for the last couple of years, there was quite some advances have been made on the celestial side. That is, of course, related because you are in two-dimensional conformal field theory. So in principle, you have this book, and of course, you have a completely different conformal field theory, celestial conformal field theory is completely different. I mean, you don't find it in this book, but you can somehow go through all chapters and think about what will change, or what can I do better, or what I need to do in order to, for example, study conformal block expansion and things like that, or in order to compute a stress tensor or Virasoro algebra and so on. And yeah, so I think it's fair to say that there was quite some advances along this line, along these lines of the book. And I will actually also show you some nice advance where this, for example, gluon amplitudes, celestial gluon amplitudes can be really written like in the way you are used to from conformal field theory, namely that 4-point amplitudes derive from differential equations, or more precisely from Kniezig-Samolotchikov equations, as you know from this book. At least I don't know much about three-dimensional conformal Carrollian conformal field theory. What I would like to know is whether there are, like what we'll find here, whether there are also some Kniezig-Samolotchikov type differential equations for correlation functions. I mean that, and I will show you why I'm particularly interested in this. So let me just also compare a little bit what we know in both approaches. I mean, celestial and Carrollian conformal field theory. So of course, when you think about conformal field theories, you think you think first, one of the first things you do is or look at the operator product expansions. And so you can compute operator product expansion on the celestial sphere. There have been proposed two approaches. You can take amplitudes in four-dimensional Minkowski space and look at collinear limits of, so we, for example, take a gluon amplitude, and you look at a collinear limit of so two gluons go collinear, which mean, okay, in four dimensions mean that the momenta of the gluon become parallel, but when you look at your positions on the celestial sphere, it means that this momentum of the gluon is mapped to a point on the celestial sphere, that these points come close together, which is exactly what you do for this operator product. And then, so you studied or you derive it from collinear limit of gluon amplitudes, and then this is what you find. So you have these operators, gluon operators. So this means you have spin 1 on spin 1. And this is this conformal dimension of these gluons, which generically is 1 plus I lambda, or 1 plus I real number, as I have shown you. And then you find another gluon with spin plus 1 here, plus regular terms. And there's some Euler beta function B here, appearing here. And then this group of people have derived it differently. That just stayed on the celestial sphere without moving or without looking at the four-dimensional amplitudes and looked at the first principles to construct this operator product expansion. So how recently in the paper by Adrien, Lionel, and Ricard, they also looked at operator product expansions and also so they looked at collinear limits and transformed them. Did this Fourier transformation I showed you before, and got this. So this is now for operators of spin 1, spin J1, spin J2, and then this develops this operator product expansion. So you see it's kind of course, you know, you have three coordinates, I mean, Z's and U's, so it's kind of looks a bit more complicated than in the two-dimensional case. Also, when you now really take gluons, like so spin 1, actually then this spin, gluons fuse into gluons. So this means that you have a J is also spin 1. So that means this is singular, this beta function. But you can, there's a trick, or there's something what you can do in on Carrollian conformal field theory. You can take Carrollian descendant, so you can take a U derivative and then you reshuffle the indices here, and then you get something finite. And I don't want to say more about this because Romar will give a talk next week on this beautiful paper, and so I don't want to. It's just I just wanted to confront this celestial OPEs to this Carrollian OPEs. Now I'm interested in amplitudes because, as you may know, I come from amplitudes community, and so I feel very comfortable when I see amplitudes. So an amplitude is you scatter particles with external momenta. So this is a 2 to n scattering. So you scatter 2 particles of momenta P1 and P2 into n minus 2 particles. And any amplitude, of course, this is a triviality, assumes this form that you have this delta function ensuring momentum conservation times some real number function which depends on this external momenta, and of course there might be polarizations which for spin 1 particles if you scatter gluons, or spin 2 for gravitons or anything else. And this is as the objects we want to study in 2 dimensions on the celestial sphere and on the 3-dimensional Carrollian geometry. So I have told you already that you do this to convert from the momentum eigenstates to the conformal primaries of celestial sphere. You do this Mellin transform. So that means now we have this n-fold Mellin transform on this n particles. And of course, now the rest we just rewrite in terms of this celestial coordinates. So this is all just a triviality so far. And the same you do for the Carrollian amplitude. Now there's this Fourier transformation. The epsilon, I should say that epsilon I takes care for the n particles, whether they are incoming and outgoing. So it's epsilon I is plus minus 1. So these are the objects. This should be some, at the end, this should be some CFT correlators on the celestial sphere. So this, which in particular means that the conformal invariant under your conformal symmetries. And these are the objects which we would like to construct by first principles on the or celestial conformal field theory methods. And the same for this Carrollian amplitude, which now depend on this third coordinate, on this retarded coordinate U. So I give you again. I need to borrow results from the other groups, from other people. So this is for how it looks for the simplest amplitudes, and for 2-point amplitudes, celestial. So you start with a 2-point amplitude in Minkowski space, which you just rewrite in terms of this coordinates I gave you for the describes the massless particles. I should say, I mean, everything what I'm doing is 3-level. So there was no loop in this endpoint scattering amplitude. So this is 2-point 3-level amplitude, just written in terms of this coordinates of this massless particles. And then you do this Mellin transform, you arrive at here. So what is the takeaway should be that there's this delta functions on the celestial sphere, which of course come from the moment conservation in 4 dimensions. I mean, from here. And now this has been first derived in the paper by Laura et al. Here, of course, it doesn't look so nice anymore because you have this. You need to regularize the integral because otherwise it's IR divergent. But it's not really a problem because, again, as I said, you can consider Carrollian descendants. So you take a U derivative, and then this term is just goes away because it doesn't depend on U. And this you can see actually is related to a kind of modified Mellin transformer. Again, so I mean, because nothing else, so from here to here and to here, we just did this integral transformation. That means in particular that you can switch between all these amplitudes they're related by combining inverse Mellin and Fourier transformations. I mean, I stress this because this is important, because once you go onto the celestial sphere, for example, you will find some non-trivial things going on, and I would like to understand whether these non-trivial things can be taken over, for example, to the Carrollian approach or vice versa. So I show you what, I mean, of course, 2-point amplitudes are trivial. So the first non-trivial amplitudes are 4-point amplitudes. I mean, there you really need to compute, I mean, in 4 dimensions, you need to look at your Feynman rules in computer. So this is by now, let's say, older results. So this is a 4-clue amplitude. You scatter 4 clues of helicity minus 1, minus 1, and plus 1, plus 1. And the only thing what you should take away is that, of course, it assumes a form which is reminiscent from your favorite book about conformal field theory. So it has this Ci minus Cj term, which ensures that this is transforms covariantly under conformal transformations. And in addition, there is this strange delta functions which mix holomorphic and anti-holomorphic sectors. So this is a conformal Grosch ratio, which you also know from conformal field theory. And yeah, so this is just how it looks like. The gravitational amplitude looks almost similar, which is kind of nice, except that there's the delta function, which has a different argument. So this is a gravitational amplitude in the conformal basis, and you might worry that when I told you that the delta i's are in principle 1 plus I some real number, so you get some constraint on these real numbers, and here you get a different constraint which is generically or a priori not fulfilled, but since this is if you treat this as a distribution, I mean, there's no problem in I mean, you can just do an analytical continuation, and then this is a well-defined object here. Mm-hmm.
What is beta?
Okay, I forgot to, it will come later. Beta is a combination of these deltas. It's a combination of this delta, yeah, it's some, yeah, sorry. What I should mention here is that so you do these Mellin transforms, and so if you do it for 4 particles, at the end you do 3, so you have to do 4 Mellin transformations, and so at the end, there's essentially there are many delta functions involved, but the last integral is usually then the omega 4 integral, and you will end up with. So you have this minus 4 plus delta from the Mellin transformation, from the formulas of Mellin transform, and then there's some energy dependence of the amplitude, and the gravitational amplitude has a different energy dependence than the gauge amplitude. So this has a positive number, so it's energy squared, the gravitational amplitude, and that makes this integral generically UV divergent, and this is exactly what related to what I told you before, that this delta function is that you don't really sit at the where the delta function is 0, but you can just consider, for example, different delta. You can treat delta as a complex number and then do analytic continuations, and then this is a well-defined object, this gravitational amplitude. Mm-hmm. I can, for example, send deltas to 0, or when I consider soft limits. So no, they're not necessarily in a spectra. So you have a principal line, which in the delta space, complex delta space, on which which is your spectrum. So it's a line 1 plus I lambda, and then this means that you need to fulfill this of this line, but it's an analytic continuation. A higher gravitational amplitudes. Yeah, it's you also have it. Yeah. Which you do also when you consider soft limits. You also go away from the principal line. I don't know, but Laura, you have a paper with that you go soft limit, do soft limits, and then you. Yeah, but analytic continuation. I haven't looked at it, but I think there should be a way to. I think it should work. I mean, I haven't thought in. I haven't started this, but I think it should work. Or at least I hope that it works. Good. I mean, just completeness. I don't want to discuss strings. I mean, or string theory, but it gives just if you do this for a string amplitude, which is a whole which comprises a whole tower of higher derivative amplitudes. I mean, higher derivative 4-point amplitudes. Then in turn you get a whole series of celestial amplitudes describing higher derivative operator or couplings of higher derivative operators. So this is interesting on just from the level of that you have a series of amplitudes, which essentially looks the same as the so this is four gluons in open superstring theory. So it essentially looks the same, but it has some additional form factor I, which is some Nielsen polylogarithm type integral, and which can be expanded in terms of this multi-zeta values. I will only show it because we also did this for the Carrollian for Carrollian amplitude, and there it leads to, I mean, and then we want to compare this two and see how it is related. And let me now go show you some samples for Carrollian amplitude. Here I have a problem because there was this beautiful paper by Romain and Lionel, and so I don't want to show. He also will give a talk next week about this, I guess. And so, but I show you these amplitudes which I didn't compute. So this is a 4-point amplitude, so-called mixed amplitude, which involves a graviton of spin -2 and then 3 gluons. So the so-called Einstein-Young-Mills amplitude. And so it looks, it's of course a function in terms of C, I mean celestial coordinate, and U, I mean the retarded time U. And of course we have 4 particles, so we have U1 up to U4, and so there's U1, U2, U3, or U4, which enters here, and this depends on this C dependence. So this is just to give you an impression how such an amplitude looks, such a Carrollian amplitude looks like. And again, there's this delta function constraining this conformal Gauss ratio R. And actually, it's in the Carrollian, for a Carrollian amplitude, is actually the more gravitational states you scatter, or in contrast to gluons, you get rid of this IR divergences. So this is, as you see, there's no regularization was needed. And I just refer you to the talk of Romain next week. There will be many more. I mean, there will be the basic amplitudes on gluons and gravitons. This is a graviton, 1 graviton and 3 gluons of helix. This is helicity, -2. -2. And for gluons, you have +-1. And I mean, I could have also studied plus, but actually the plus with plus it would be 0. Yeah, you have a representation for the polarization tensor in terms of z's. I mean, you have your P, you have a massless particle, I mean, like graviton or gluon, for which you can compute this zeta, and then you need to define a polarization tensor which fulfills transversality, so which polarization tensor xi. So you need to construct a vector which fulfills psi, which carries the polarization times the momentum is 0. And then this psi, of course, if you have a graviton, it has two indices, psi mu, and then you contract it, and for a gluon you have a 1, and then you construct it, express it in terms of the C's, and then at the end you will see these C's on the right-hand side. Yeah, you just need to fulfill this equation. I mean, there are several choices. I mean, it's not fixed. It's not unique. But the amplitude is, of course, unique because of gauge invariance. So now, just for how does it look for the string amplitudes? I mean, this is Carrollian amplitudes. Again, it will give you a whole series or set of Carrollian amplitudes, which might be interesting on their own. So, I mean, as I said, I don't want to study strings, but they will give us. So, next to the Young-Mills amplitude, again, I scatter gluons. So we have the Young-Mills amplitude, the Carrollian Young-Mills amplitude, which Romain will show you how it looks like. I mean, it was again some function depending on U and U's and Z's, but as I said, it will be IR divergent. And then we have this finite term set of terms, which is at this point it's just a power series in two variables k and l. So it's, and again there's this transcendental numbers up here, this multi-zeta functions as a coefficients here, which I find interesting because actually these coefficients are related to the Drinfeld associator. They are coefficients of the Drinfeld associator. And so what is a Drinfeld associator? It's when you study KC type differential equations, they have monotromies, and you can, out of these solutions, you can construct a unique solution without monotromy by taking a ratio. And this is the Drinfeld associator. And this Drinfeld associator has a power series expansion, which coefficients are given in terms of these objects. And this is because in a moment I will study, I want to worry about this, or want to study underlying differential equations for this Carrollian and celestial amplitudes. So I find this very interesting because this might already ring a bell that there might be some differential equation behind this Carrollian amplitudes as well. And from the string side point of view, this is, I mean, in string theory, you have an infinite tower of massive states, which depend on the string tension, inverse string tension alpha prime. And at the level of this Carrollian amplitudes, this gives you an infinite series of higher derivative Carrollian, higher derivative couplings, which then are described as these Carrollian amplitudes. Not here because it's finite. Because yeah, it's because we have higher derivative. So it's we don't. I mean, this for this. Yeah, we have this is the Carrollian gluon amplitude, which is in your paper, which is has this regularization. So if you want to get rid of this regularization, you need to consider U derivative, but not here. You don't see any regulator here in the second line. This comes because because the string does a regularization for you. The string world sheet, or let's say the alpha prime. This factor here. But you can, of course, write it in terms of U descendances. So by just doing some manipulation, you can write it in terms of a infinite series of U derivatives. But you don't need to do it in order to get rid of IR divergences from here, because there are simply no. But if you want to write or see how this is related to U descendants of the Young-Mills, of the Carrollian Young-Mills amplitude, you can write it like that, which, I mean, you might say doesn't look so nice. Are there further questions on this? Amplitudes? Is it straightforward? It only, presumably only works for the 4-point amplitude and not, it's essentially related to the fact that, so this is for superstring scattering, which is related to the Veneziano amplitude, which is related to Euler beta function. This Euler beta function can be related as an exponential. But when you go to 5-point, you have Gaussian hypergeometric functions, which generally cannot be written as exponentials. Yeah, that is what it should do. Should do, because then you decouple strings. And yeah, good question. So alpha prime goes to 0 means that it's infinite tension. So all string states become massive. So you decouple them, and then you get this function. I mean, there's a damn nice thing about here. You see that the alpha prime enters here in this power series, so it mixes this coordinate dependencies on the u coordinate, while on the two-dimensional case, on the celestial sphere, the alpha prime is just factorized. So that of course has to be because you are in the two-dimensional conformal field theory. So and alpha prime is a mass dimension, so it should not enter in this. So it can only enter as an overall factor here. So this is kind of, let's say, a proof that this result must be in some way correct, because alpha prime is really factorized here. While in the three-dimensional case, it gets mixed into this power series with the u coordinate. So now I want to come to how to unify these pictures, or how to what we can do, or what we to understand from this looking at these amplitudes, to understand the underlying conformal field theories. So both for 2 and 3 dimensions. Now I want to tell you some facts what we have found for the two-dimensional, for the celestial amplitudes, or more precisely for the celestial gluon amplitude. Well, the first thing what we have already seen is that there's always this, for the 4-point amplitudes, is delta functions which mix the holomorphic and anti-holomorphic cross ratio, which means that cannot be standard conformal field theories, because I mean, when you in particular look in this orange book, I mean, there's always a decoupling at tree level between holomorphic and anti-holomorphic sector. At tree level, I mean, at one loop, the sectors couple. Even, I mean, for example, in string theory. But so this is means that it's non-standard conformal field theory. And now we want to see whether we can have still some ordinary conformal field theories which compute or which describes these amplitudes. And ordinary conformal field theory means that we have minimal models with Mino-Witten models, that we have 2- and 3-point correlation functions of primary fields are determined by conformal field theory, and then the 4-point amplitudes are determined by the corresponding, or by corresponding partial differential equations. Corresponding means corresponding to the underlying theory, which generically are Kniznik-Samolotchikov type equations. So we would like to see, or to answer the question, to what extent first, celestial amplitudes can be described or derived from KC type equations, but I think one should ask the same question for the Carrollian amplitudes, if I want to proceed along this, which give for the celestial amplitudes some interesting results. So how do we what differential equation should we discuss, or how do we get a differential equation which eventually give us this, the amplitudes we have studied? There's this, you can easily derive this differential equation, which, I mean, I didn't introduce a notation. This is helicity, so it's related to when you write this Lorentz vectors into spinor helicity basis. So it's just a differential equation, and don't worry what it is. So it's it's a first order differential equation, and we write them, you can write them in terms of celestial coordinates. So that you have now operators with, acting on the celestial sphere, and there's also operators with respect to this delta. This is, of course, now looks already like a KC type equation. So that means you get by free from this equation, you get a linear differential equation on the celestial sphere, and which has been derived by this Banerjee and Gauche. The first thing you can ask, of course, now when you go to Carrollian, can I have a similar differential equation derived on Carrollian space, which, of course, now you should not have this derivative with respect to conformal dimensions. There should be some U operator in the second line. And then maybe you can proceed in the same way as I now do for the Carrollian case by solving this differential equation and then seeing something interesting. This might be a nice project for somebody who is looking for a project. So do what I do now, say in the following on the Carrollian space. So we solved this differential equation on the celestial space, and we got this answer. So with Tom Taylor from Boston and Bin Su, who is now a postdoc in Edinburgh. So it takes a very nice form. So for people in the amplitude community would like this very much already. This is so this is for Kluon amplitude, and then these are the structure constant of the underlying QCD gauge group, and these are these positions in celestial, differences C1 minus C2 and so on. And this is a called Park-Taylor factor, and then there's an additional factor which is independent on the gauge structure, which is reminiscent from Coulomb gas description in the Orange book. It's a complex integral. So actually, this complex integral can be written after some massage in terms of such that you can you write it in terms of your celestial coordinates, and there's of course some ambiguity because you solve this differential equation, which is governed by this source term, by this integral dx4 term, which can be interpreted as a dilaton source to this 4-Kluon amplitude. So you can, there are some choices for this dilaton source, but this is now just a solution how it looks like. This of course looks very much like this is the Mellin transform of this 4-Kluon process, and in addition with this dilaton source. Yeah, this is Young-Mills coupled to dilaton in the dilaton background. Yeah. The background is changed because this changing removes the delta function. But this is similar to what for example, is done in minimal models, that when you describe them with Coulomb gas description, there you also have a correlator and which has to fulfill some, or where you have background charges. Okay, yeah. So we solve this. So this is the Kluon amplitude, and now we transform it into celestial coordinates. Now here you don't see yet the dilaton, so this is just a differential equation. You solve it, and then you have you can solve it in the old. You can solve it and see the the celestial amplitude with a delta function, but there are other solutions with this dilaton, which then can interpret as a dilaton source. Yeah. So you can.
How do you connect?
We look in the four-dimensional space and how this amplitude looks like. It looks like then the four gluon. I mean, it looks like the 4 gluon amplitude plus dilaton. When this is the amplitude in celestial coordinates, and then we. I mean, you see the J is it will be we can. It depends on what solution you want to discuss from your differential equation. So, yes. Yeah, I want to avoid this delta function. And then we find a solution which, so to say, a nice solution, which we want to study further, which avoids this delta function in particular.
Can you say more about the nature? Is that just
no, it's classical. So this is 3-level. This is trivial to derive. I have to say. This amplitudes in 4-dimensional Minkowski space. When you work in spinor helicity techniques, you have there's this BCFW rules from which you can derive these amplitudes. They involve some kind of shifts and you do this a complex shift in the momentum, and if you do look at this complex shift, you can derive some consistency conditions which give you this equation. Yeah, you can, or like some consistency condition, yeah, some like a Ward identity. I mean, there's this shift symmetry that you shift momenta of your external particles. So you have, for example, a momenta you shift by pi plus z. ZP0, for example, and then for the another particle you shift pj plus minus z pi 0. So you don't you fulfill momentum conservation, and then if you put this into the amplitude you get some consistency condition which give you this.
You know the loop correction?
No, I don't know the loop. I think I haven't been. Yeah, but when you do loop BCFW in loop integrals, it's unitary cuts, and then you essentially cut it. You essentially construct it from three amplitudes. So yeah, it might be interesting to see, or it might be possible to derive something at loop similar, but this has not been done yet so far. And so then this at loops, I know there's a loop, or there's a loop, and then there's KCB, Kniesnicker homological of Bernard equation, which was in the string case describes loop integral. So maybe then this is what the right thing at loops. I think there's not. There is not. I haven't followed it since that time, but I think there was not anything generalizing this to loops since then. So this is what our solution, which, okay, it has some arbitrariness and described as a Dilaton source. And actually we liked it because we did a lot with this Carrollian amplitudes and wanted to get rid of these delta functions. And I mean, there are other ways like shadow transforms and so on. And this led us to, after looking this Orange book, to Coulomb gas formulations. And then somehow it's kind of comes back here that we have now amplitudes where you have an additional background charge, just like in the Coulomb gas formulation. So the Dilaton source might play the role of a U1 background charge in Coulomb gas models. And and now we can see, let's take, is there some particular or nice choice of J such that the amplitude have a nice interpretation in conformal field theory? I mean, in standard, let's say, conformal field theory, I mean, Liouville conformal field theory, where you know how to derive things and so on. And this is done, okay, let me briefly introduce Liouville theory on 1.5 slides. So we consider Liouville theory. So we have a complex field phi, and there's a Lagrangian, and there we have a background charge which can be parameterized in terms of this B. And the central charge is given in terms of this formula, and then we have operators, primary fields, which are given in terms of this as exponential of this field. So it looks a little bit like what you do in Coulomb gas formulation. I mean, there you also have this exponentials and background charge at infinity. Now we can consider correlation functions of these primary fields, and as I said, we need to saturate or develop or supply a background charge. I mean, there are several possibilities, I mean, infinite possibility essentially. The simplest one is just to have one of this operator supplying the charge 1 over B, and then you have to saturate, you have to fulfill this condition that the sum of U1 charges, so alpha I plus this charge is the background charge Q. So, and now if you want to solve this, so Q is given in terms of B plus 1 over B, so the 1 over B cancels. So if the alpha I are B times sigma I, then this equation is fulfilled. So that means your alpha i's here in these operators are given in terms of B times sigma I. Now you can compute the dimension of this fields, H plus H bar, and that tells you, or that is why we take B goes to 0 limit, because we want to somehow connect this to this celestial primaries, or this to the lambdas more concretely. And of course, B goes to 0 means that we have infinite background charge and infinite central charge. So we have a Liouville theory at this particular values. Okay, now just continue with Liouville theory. So we have this correlator IN, and we do some non-trivial computations on this integral by borrowing some results of Stephan, and we can simply write it. So this is simply after some tedious algebra, we can write it in this Liouville correlator in this form, which now looks very much like a Mellin transform on these energies. And there's this 1 over Q squared, which is given in terms of this expression. And now compared to what we have obtained from solving our differential equation, we had this object here. And now you can ask the question how and for what choices this expression corresponds to this. And of course, if you take this source, so you have some kind of, which corresponds actually when you look in the four-dimensional picture to a dilaton shock wave, then you can relate this expression to this Liouville correlator. And I mean the Q, so what is going on at the level of the Feynman diagram in 4 dimensions, the 1 over Q squared. So if you look at this, this is just P1 plus P2 plus Pn, or in that case we have 4-dimensional. It's just a propagator, of this n particles to this background here. I mean, so it's 1 over P1 plus Pn squared. So this is how the dilaton couples to this amplitudes.
Could you see
that? From the amplitude, when you there's an amplitude for n plus 1 point amplitude, so n gluons plus 1 dilaton, and this takes exactly the form such that you have this in the celestial coordinates. It assumes this form. In other words, the amplitude with n gluons plus 1 dilaton assumes the same form as the n gluon amplitude, which is, I mean, this is called Park-Taylor amplitude. Only that you relax this momentum conservation. So in a way, dilaton as scalar is the simplest way of deforming this scattering process. Okay, I guess I'm running out of time, but I'm finished in a moment. So I just summarize now what we have obtained. Is we have this celestial gluon amplitude. So we scatter this 4 gluons, and we have found that by solving this differential equation, that it can be written like in a form like in a factorized form with a current term and something like which is generic to gauge sector, and then some universal complex integral. And so this they're given here. So this was this gauge theory, or gauge. It looks like a gauge correlator. And then we have this complex integral, which we could interpret as a Liouville correlator. Which now I write down explicitly what we have chosen. So we have this Liouville, this background parameter saying the background charge of the Liouville theory, and we have these operators, and they compute for us the integral which appears in this gluon, the celestial gluon amplitude. And this is actually very reminiscent this this C1 2 to the 4 is reminiscent what this has been found by these two people when they studied the gauge correlators. I stress this because when you look at string theory, or you only expect the denominator term, but not this strange C1 to the 4, but this seems to be related to this work of Costello-Paquette. So what we have found is that celestial amplitudes now, if you evaluate them in the presence of a dilaton background, that they can be described as some correlation functions in Liouville theory with light. Light means because the P goes to 0. Light Liouville operators times some holomorphic gauge factor. And there was a paper a few weeks ago by Strominger et al. Who I think adopted this idea of Liouville CFT and discussed it in terms of celestial leaf amplitudes. So that means this Liouville description might have might have a more universal presence in the celestial case. And as I said, I always stress that you might go through this integral transformation from celestial to Carrollian. And I mean, there's clearly must be some differential equation of the type I showed you in the celestial coordinates, some KC type equation in Carrollian coordinates. So then, in principle, it should be possible to go to do the same steps as before, and find some non-trivial KC equation in Carrollian coordinates, and then interpret this Carrollian amplitudes also, or embed them in some background, and which then might give maybe a better explanation why this Liouville theory. So we might then understand this Liouville theory from the Carrollian setup maybe better. And other thing, of course, the Carrollian case is also the more interesting case to study, for example, a flat space limit of ADS CFT. So that's, but there's of course many things to be done. And there's another thing which that actually was why I showed you this string amplitudes. There's something nice going on which we continue. We have originally seen. I mean, in the work with Tom Taylor, we have seen for celestial amplitudes. For the celestial string amplitudes, but we see it also now for the Carrollian amplitude. So I mean, I will end with this slide. So for the celestial amplitude, so this is a celestial string amplitude. It depends, of course, on the coordinates z and on the deltas, or which also lambda, so celestial gluon amplitude in string theory. And if you send all the sum of these dimensions to infinite, the celestial amplitude is receives only a contribution from a subtle point, and the subtle point is this point on the celestial sphere. The analog limit on the Carrollian case is that you send the u coordinates or one of the u coordinates to infinite, so one of the 4 u coordinates, and then again the Carrollian amplitude is receives only a contribution from the subtle point on the celestial sphere, but this subtle point actually is the same subtle point which appears when you do the alpha prime, the high energy limit in string theory. So that means, so in string theory, of course, you have a string worldsheet which computes this amplitude, and then this means that you are it receives only a contribution in this limit from one subtle point, which is the same subtle point as you have here on the celestial sphere. So there might be it looks like that. I mean, there's clearly a relation in these limits to the high energy limit of string theory. So though then in string theory you have vertex operator positions, and then they become points on the celestial sphere. But it might mean that there's something more fundamental when you go away from this high energy limit, that maybe when the celestial and Carrollian amplitudes that they might be embedded into some more fundamental theory, which could be string theory or something else. But I find this coincidence nice, that at least in this high energy limit, the celestial spheres becomes a string worldsheet. And yeah, this is, I want to end. Thank you.